Okay, let's go over the third chapter in terms of just the textbook. I already went over the third chapter here, over here, but this is the third chapter of the um textbook. So inside this chapter, it was talking about multivariate, discrete distributions, and independence. Many of these concepts were already covered in the second chapter, actually. So I'm just going to walk you through all of the things I translated into English again. So we have joint probability mass function, which is just the idea that Pxy is equal to Px equals x, Py equal to y. That's just the definition. We can get the distribution of Px just by summing up the y's, and then the y's by summing up the x's. The expectation in the multivariable case would just be um, of E of g of x would just be the sum of the g of xy and then their probability. And of course, it's linear, so then you can just basically extract out the a in front and the b in front because they're constants, and then the expected value of x and y, regardless of whether or not they're independent, can be broken up. And then the third part talks about independence of discrete random variables, which basically means that if they're independent, then I can just break it up into their products types together. And it's a if and only if. So if they can be broken apart, then they're also independent. And then if they're independent, I can break it down like this. Pretty straightforward. And it's the same with expectation. I can break it up into, if they're independent, I can break it up into expected value of x is equal to expected value of y. But it's not necessarily the same case when I go backwards. Um, and then the other theorem is that I have the expected value of two functions. Then it could just be the functions applied for each one. Those are pretty straightforward, I'd say. And then the convolution formula is if x and y are independent, the mass function z equals x plus y, then p of z is equal to sum of x, p of x, and then y is z minus x. So it's pretty straightforward. You just add back whatever thing you need. So then y is just z minus x. So the importance of this convolution formula is that it basically means Poisson still follows Poisson, and some of binomials variables still follow a binomial distribution. And the last part is indicator function, which I also already talked about, which is the idea that like it could either be 0 or 1, kind of split apart by where is it? Um yeah, it's pretty far off. Okay, here. It's basically the idea that I have an indicator function and I can have one in one condition and 0 if it's the other condition, sort of that idea. And then the basic properties is that, yeah, okay, if it's n, then I just have to multiply it. If it's the complement, then it would just be together, added up together would be 1. Because the probability sum to 1. And then the expectation would just be the probability. And indicator function is pretty useful in inclusion, exclusion, or whatever time when you have a binomial distribution. You can split it up like that. Okay, let's end off here.